Welcome to GTC 2020. My name is Rick Schweet, and I'm the founder, president, and CEO of Kinetic Vision based in Cincinnati, Ohio. My presentation today is on the use of true digital twins to develop, test, and optimize complex systems. So what is a digital twin? Well, Wikipedia says a digital twin refers to a digital replica of potential and actual physical assets, processes, people, places, systems, and devices that can be used for various purposes. So how are current digital twins used? Typically, digital twins utilize simulation models, machine learning, statistical analysis, or combinations thereof, with sensor fusion to predict needed maintenance and minimize failure probabilities. These digital twins are black boxes that produce intelligent output based on the complex data they receive. True digital twins replicate all aspects of the physical equivalent, including the three-dimensional environment, physics, machinery, robotics, vehicles, and other devices, software and machine learning systems, connections to external networks, and importantly, human action and interaction. So what are the advantages of using a true digital twin to develop some system or process? Well, virtual spaces and objects are much less expensive and time-consuming to create than their physical counterparts, typically by 2 to 10 times. One example is the creation of training data for machine learning models. Because the twin accurately represents the physical system, this data can be created synthetically. In this example, an image from a store shelf camera has bounding box annotation depicting in-stock items. The 100 annotations in this image might cost $5 to $10 with manual labeling. The synthetic equivalent is easily 10 times less. In addition, rendering synthetic training data sets is dramatically sped up with the use of GPU rendering. A 100 to 500 times improvement is typical. This might be irrelevant for a single image, but consider that 10,000 images might be needed to train a model for one store section. And creating the annotated data set for an entire store could easily require the rendering of millions of images. So maybe I've convinced you that developing your system or process virtually lets you innovate and optimize much faster, while at the same time dramatically cutting the overall development cost. Your next question might be, okay, I'm sold, but how do I do this? Well, one route would be the Star Trek Holodeck. Yeah, the Holodeck isn't quite here yet. But some notable companies have made considerable progress utilizing digital twins. Amazon Go is reported to have been developed physically at much time and expense, but has publicized that digital twins were also utilized. And of course, NVIDIA is a leader in this area with its Drive and Isaac platforms. So if this is so great, how come true digital twins aren't routinely used for system development? Well, there are some roadblocks. The main one being that digital twin development requires collaboration between many disciplines, including design and engineering, CGI artists, and game, VR, simulation software, and possibly machine learning developers. These folks are often located in different groups in different facilities, states, or even different countries. Most companies are not organized to easily bring teams like this together. In addition to specialized people, you also need specialized tools. A digital twin development system should be GPU powered, as simulations must run in real time to be usable. If machine learning is involved, that training is most effective on multi-GPU systems, which can be local or cloud-based. So we're not quite to the holodeck yet, but we're getting closer. Today I'm presenting 3 examples: an automated product inspection system, a hospital surgical suite, and a camera-based retail AI system. The first example is an automated system to receive just-in-time shipments of automobile oil filters, perform a quality inspection using industrial computed tomography, and route the accepted products to the manufacturing line. This is the 3D virtual environment showing the incoming product shipments, CT scanner, and conveying of qualified products to production. The entire system's design, optimization, and testing was done using this environment. Commercial simulation software drove the robot in the twin. The robot's motion can be connected in real time or pre-recorded. Here's a side-by-side comparison of the twins during qualification testing. The physical robot was programmed in the digital twin to pick the incoming oil filters, place them in the scanner, perform the scan, and remove the filters. Those that pass the inspection are routed to manufacturing, and those that don't are collected and returned to the vendor. All system development was done virtually in the digital twin before any physical testing. Imagine doing all this physically and moving a 15,000-pound CT machine around. Another benefit of a true digital twin is that other key stakeholders, such as management, training, and safety teams, can be involved throughout the development process. All they need is a VR headset, as shown here, and they can drop in and evaluate the system at any time. This greatly enhances team collaboration and minimizes the chance of expensive and time-consuming misunderstandings. Nothing can replace actually being there during the system development, and a true digital twin enables that. In my next example, a new surgical suite is being developed, including room configuration and equipment layout, and new device concepts and new procedures are being evaluated. The surgeon avatars are driven in real time using concurrent motion capture, allowing true subject matter experts to be present in the digital twin. The subject matter experts, in this case surgeons evaluating a new procedure, experience the twin through virtual reality. They feel just like they're in the actual space. Their motion, including hands and fingers, is tracked in real time, as is the position of all objects in the scene: the patient, equipment, tables, and medical devices. New devices can be evaluated virtually. They just need to feel and act like the proposed device, but complex functionality is done virtually. A 3D printed model with a spring-loaded trigger can digitally replicate a prototype that would take many months and $50,000 or more to create. Device design iterations take hours or days instead of weeks or months, and the subject matter experts can be located anywhere in the world. Here, a composite of the surgeon headset views, motion capture process, and digital twin third-person camera are shown. Room configuration, equipment layout, procedures, and devices are all tested virtually, allowing for iteration and innovation to occur at a much faster pace. Although not shown here, it's even possible to simulate actual human tissue and procedures for training and to evaluate medical device concepts. In this example, a retail AI system is being developed with the goal of using in-store cameras to monitor and detect shopper product selections. Project goals include the creation of synthetic training data, training deep learning models, and testing model performance using real shopper behavior. First, the synthetic training data for the AI model is created using the virtual environment. The dataset consisted of 20,000 segmented product images using domain adaptive and domain randomized data in a 50-50 split. Once the AI model is trained, it's time for virtual shopping. Here an avatar, driven by concurrent motion capture, shops in the virtual store. The human actor wears a VR headset and sees the room, products, cart, and even her own hands and body exactly as if she was shopping in real life. The in-store camera is also replicated, as its location and functional parameters are part of the study. Here the machine learning model is being tested in the digital twin using the pre-recorded avatar motion. However, the AI model can also be tested in real time. Actual video of a test shopper is shown on the right. The model's performance is very good until products are placed in the cart, where detection fails. What's important, however, is that the twins behave similarly, and the virtual system mimics the physical outcomes. It was surmised that the in-cart detection failed because no images of carts or products in carts were included in the deep learning training set. An additional 10,000 images were generated to include the cart in random locations with random products in it, and the model training was continued with this new information. The resulting in-cart detection was improved to an acceptable level. In summary, a three-step process was utilized within a digital twin to train, test, and optimize a retail AI system. First, a synthetic training dataset was created and used to train a deep learning model. Next, a virtual shopper avatar, driven by concurrent human motion capture, selected products and placed them in her cart. Finally, the trained model was tested and optimized. Most importantly, the digital twin closely mimicked the physical system performance. A system deficiency was discovered, but it would have never reached the physical testing, as it would have been identified and remedied within the digital twin. So what's a true digital twin? Well, currently it's the closest thing we have to the Star Trek Holodeck. We can effectively replicate 3D environments, functioning machines, robots, and devices, and the software to control them. We can train and test machine learning systems and have real humans accurately interact with our virtual world in real time. The relative ease of creating a virtual reality instead of a physical one empowers accelerated innovation and optimization, with dramatically decreased development time and improved stakeholder collaboration. Commander Riker would be proud.